Hello everyone, welcome to lesson 8-1, function tables. In this lesson, we are going to try to answer the question of how are symbols such as less than, greater than, and equal to useful? And some of the words we will be looking at are function, function rule, function table, independent variable, and dependent variable. Real world link, science. A ruby-throated hummingbird beats its wings about 52 beats per second. Make a table showing how many times this bird beats its wings in 2 seconds. So this is the rate. And now we have to just multiply the rate by time, right? And it's 2 seconds. So number of seconds is 2. And we can write an equation. The number of seconds need to be multiplied by the number the wings beat per second. So if it gets 52 every second, it's going to be 52 times 1 second. 52 times 2 seconds. And there it is. And that would be, our answer would be 2 times 52 would be 104. So at the same rate, if the bird can maintain that rate, in 2 seconds it will have beat its wings 104 times. And this is the essential skill for this lesson. We have to create these tables. Make a table to show how many times it beats its wings in 6 seconds. So we have the number of beats per second there. Sorry, the number of seconds here, which is 6. We have to replace the variable seconds. As we replace it with 6, and we multiply it by 52. So we do the quick math on the side. 6 times 52. 6 times 2 is 12. Carry the 1. 6 times 5 is 30. Plus 1 is 31. So we get 312 beats in 6 seconds. Continuing on. Make a table to show how many times it beats its wings in 20 seconds. So number of seconds is 20. We replace our variable seconds with 20 times 52. Okay. Now this is essentially like the first question because we have 2 times 52, but we have to add in that 0 to our product. So we know that 2 times 52 is 104, correct? And if we add in this 0 here, because it's not times 2, it's times 20, we get 1040. A giant hummingbird beats its wings about 10 times per second. Okay, 10 times. Make a table to show how many times the giant hummingbird beats its wings in 3 seconds. So it's 10 times every second, right, per second. So in 3 seconds. So number of seconds again, we plug it in, 3 seconds, and now it's times 10, so it's 3 times 10, and we get 30 beats in 3 seconds. Find the output for a function table. So what is a function? A function is essentially a rule we must follow in order to get our product or our quotient, the answer, essentially. So what is the process? What is the computation? That is essentially what a function is. A function is a relation that assigns exactly one output, what you get, your equal sign, value to one input value. The number of wing beats output depends on the number of seconds, our input. Now, our input, everybody, is chosen. We choose how much time we want to measure, how much time we want to count for, right? So because we choose the input, our input is independent. But our input will change our output because if we, let's say we decide to only count for 1 second for the giant hummingbird, it's going to be 10 beats. If we decide for our input that we're going to do 3 seconds, our output will then be 30 seconds. So you see our output is changed by our input. So our input is independent and that makes our output dependent. So the function rule describes the relationship between each input and output. You can organize the input-output values and the function rule in a function table. This is just a tool for us to make everything very clear. In a function table, the input value is also known as the independent. This is the number you choose. Since it can be any number you choose, the value of the output depends upon the input value, as I mentioned. So the output value is known as the dependent variable. Let's look at more examples. Again, the function is the rule, okay? So here we have our input, and it's going to be represented by x. So every time we see x, we're going to replace x with this. This is our function, our rule, what we have to do to each input number. And then after it's gone through this, we generate an output. Okay, so we have 10, we replace the x with the 10. 10 plus 7 will be 17, as you see here. And then 12 plus 7 will be 19. And then 14 plus 7 will be 21. Do you see when we fill it in? The function rule is x plus 7. Okay, that's our function, what we're going to do to our input number. The output is 5 times the input, 5 times the output. So that means we have to multiply whatever we put in, we have to multiply by 5 because it's 5 times larger. Complete the function table for this relation. The function rule is 5x, 5 times. Multiply each input by 5. Here we go. So our input, again, these are numbers we just choose. We choose these numbers, but they have to go through our rule, and that generates a product, our output. So when we do so, okay, we do have to put our 8 here, put our 10 here because we're replacing the x, right? This is our variable that we choose, and we get 5 times 8 is 40, 5 times 10 is 50, and 5 times 12 is 60. So you can see how it changes when we change our input. Independent, dependent. If you think you got it, please go ahead, pause the video, and draw these two tables. Draw table A and draw table B. Fill out the tables, and then play the video again to check your answers. Pause now. I hope you paused the video. Let's check A. So our input is 4. Our function is whatever we choose, which is our x, our inputs, minus 4, and that'll generate our output. So let's just replace the variables. So we have 4, this 4 right here, is replacing the x, minus 4. They're all minus 4, right? Everything's going to be 4 taken away. So here we replace the variable with 7, and here we replace the variable with 10, as you see. Okay? And then we go ahead and generate an output. So we get 0, 3, and 10 minus 4 is 6. Let's go over to B. Okay, it looks like our inputs have been chosen for us, but these are a number, again, that you can choose depending on whatever it is that we're counting or doing, if we're measuring time, distance, whatever we're measuring. So, and it looks like our output is 3 times larger. So we're multiplying our input times 3. So it looks like we're going to do 3 times a number each time, correct? 3 times a number each time, because that's what they're telling us here. So 3 times 0, 3 times 2, 3 times 5. 3 times 0 is 0, 3 times 2 is 6. These are supposed to be dots. 3 times 5 is 15. Okay, I hope you got all those answers correct. Let's go over to the next page. Let's look at our second key point for this lesson. Find the input for a function table. So now they want us to put the input. They're going to give us the output. They'll give us the rules. So essentially, we're going to work backwards. The input, which is our independent variable, and output of a function table can be represented as a set of ordered pairs. Okay, ordered pairs when we're graphing, like what is your x and what is your y, and so on. Or simply a relation. In this lesson, the x values represent the input and the y values represent the output. That means the x values are independent and our x values are our dependent. Independent, dependent. This is our domain. These are names I'm going to use later on in the lesson. Domain, and this is our range. Okay, domain is what we choose, and our range is how our number changes in a range, in a set of numbers. Okay, let's look here at number 3. Okay, we have find the input for the function table. So here, this value is 3 times the value of this. Can you see that? So if we multiply times 3 to get here, what should we do to go backwards? What is the opposite of multiplication? It will be division. So I'm going to take the 6 that I have right here, okay, and I'm going to divide it by 3. So I wrote that wrong, but I'm just trying to show you like in the direction that I'm moving in. So the way we would want to write that is actually by writing the reciprocal of the 3. So it would look more like this. It would look more like 6 times 1/3. Okay, 15 times 1/3. The reciprocal, remember the number flipped? Okay, and 21 times, again, 1/3. So what is 1/3 of 6? 2. What is 1/3 of 15? 5. What is 1/3 of 21? 7. Okay, you can pause the video and read this to work backwards, and you can see, and they can show you what we just did. They want you to divide, so 6 divided by 3, 5 divided by 3, and 21 divided by 3. We could also just multiply by the reciprocal. Okay, so using the backwards design method, let's solve for x in each one of these. Now, as you can probably see, right, we would have to work backwards. So we have the 1, which is our output. We would have to add 1 and then divide it by 2 to get our input, because our input was multiplied by 2 and then 1 was taken away from it to get the 1. If that makes sense to you. So if we work backwards, we have to do the opposite operations. Or another way to do it is that you would have to, let's do it here, you would have to write out an equation. So 2x minus 1 is 3. It's 1. That's what they're telling us here. 2x minus 1 will give us an output of 1 without knowing what x is, right there. We can just simply solve. We can isolate by inverting, all right? Or you can also use addition property of equality. And we would add the 1 here, so that the 1's got from there, and it makes that 2. And then we just have 2x left, and we divide both sides by x, division property of equality, and x is 1. Okay? So x would be 1, right there. If we do the same thing with the 3, okay, let me just erase what I drew there. We get 2x minus 1 equals 3. Again, working backwards. Isolate by, we're trying to isolate the x, so we'll get rid of the addition and subtraction first, and then multiplication division, because we're working in the reverse order of BEDMAS. So again, I add the 1, I get 4, so 2x, right there, right? 2x equals 4, divide both sides by 2, division property of equality, and I get x equals 2. There it is. Okay, and again, we have 2x minus 1 equals 5. That's our output, right? So we write it out as 2x minus 1 equals 5. And then we go ahead again, and we are going to, in reverse order, try to isolate the x. So isolate by inverting. This becomes plus 1. So now I have 6. And I have my 2x, which I bring down. 2x equals 6. Divide both sides by 2. And now I get x equals 3. There we go. So those are my independent variables, 1, 2, 3, my inputs, and my outputs are that. So when I follow this function, that's what I get. Okay, so I hope you had the same answers. Let's try B, or D, sorry. Please pause the video if you haven't completed D, and then play the video to check your answers. Pause now. Okay, I hope you paused the video. I'm going to just go right ahead and write them out in here. 3x plus 2 equals 17. 3x plus 2 equals 20, and 3x plus 2, plus 2, let's erase that, equals 29. Okay, we isolate by inverting. So invert, this becomes minus 2. I get now 15. Okay. And I get 3x equals 15. Divide both sides by 3 to isolate the x. And I get x equals 5. Right? Because 15 divided by 3, right here, is 5. So x equals 5. So I get 5. Then we keep going, invert again by isolating, bring it over here. I get 20 minus 2, which is 18, right? So I get 3x equals 18, divide both sides by 3, and I get x here, right, equals 18 divided by 3, which is 6. Again, invert, bring the plus 2 over here. I get minus 2, which equals 27. So 3x equals 27, divide both sides by 3, and I get x, because this is cancel each other out, and now I have 27 divided by 3 equals 9. There you have it. And here we have another example. As we keep solving with our function tables, okay, where we have an input, which we choose, 2, 4, 5, and then we multiply that by our function. It's 70x. We replace the x with our input, right? We generate an output. X and y can be graphed as x and y. These are our coordinates. So if I have 2 and 140, I go to 2, which is my x, horizontal, and I have 140, which is very close to 150 there, you see? So 2 and 140. 4 and 280. 4 and 280, between 250 and 300, right there. And then finally 5 and 350, right there, right at the crosshair. Okay, remember, we always move horizontally before we move vertically. So we run before we rise. And here's our last example. Let's read through it. Brianna bikes 12 miles per hour. 12 miles per hour. This looks like a function, a rule. You see that? Because it's a rate of change. 12 miles every hour. 12 times h, or 12 times x. Okay? And x being the number of hours. The function rule that represents this situation is 12x. Right? 12 times a number. Where x is the number of hours. Make a table to find how many hours she has biked when she has gone 12, 36, and 48 miles. Then graph the function. Okay, so 12 miles, here we go. We have 12 miles, right there. This is the number of miles she's gone. This is the number of miles. This is our output, 36 miles and 48 miles, right? And we know that it's number of miles each time per hour. Okay, so let's just zoom in here for now. Okay, this is how far she rode each time. But now we have to solve how long did it take her to do that, because it's 12 miles per. So we already know the first one, right? Because if she's doing 12 miles per hour and she only did 12 miles, that means number one must be that. But we can also write it the way we did before, where we do in reverse, where we can write our equation 12x equals 12. Divide both sides by 12, and we get x, right, equals 1. So our first number is 1. Again, 12x equals 36, where we divide both sides by 12 again, right, because each hour is 12 miles, right? We divide that and we get 3. Over here, she wrote for 3 hours. And then finally, 12x equals 48. Divide both sides by 12. And x equals 4. 48 divided by 12 is 4. Okay, so going back, right? So in 1 hour, this is our input. She rode for 1 hour. She chose to ride for 1 hour. At the same rate, she got 12 miles. In 3 hours, she rode 36 miles. And in 4 hours, she rode 48 miles. Now, our order pairs will look like this. These are all our x's, and these are all our y coordinates. So for my first set of coordinates, I have 1 and 12. For my next set of coordinates, I have 3 and 36. And for my last set of coordinates, I have 4 is 48. This looks like a constant rate of change. Okay, so let's graph it. Okay, here we go. So I'll try my hardest to do 1 and 3. So x, 1, 3, and here's my other one, 4. And we're going to graph them vertically. So I do remember that it's a rate of change of 12. That is my unit rate. So at 1 hour, we get 12, which is just about there. I'll put a dot just about there. Okay, and we said that that is 1 and 12. At 3 hours, we 36. 36 will be just above the 35 there. Right, so that's 3 hours at 36. And again, I'll write down 3 is 36. Okay, and then finally at 4 hours it was 48. 4 hours 48, just before the 50 right there. Right there. So 4 hours is 48. And there's my set of coordinates. Okay, I hope that makes sense to you. We just took rates of change, identify our input and output, and created sets of coordinates so that we can plot them on the coordinate plane. And here we go. Here is the guided practice. So please go ahead, take a look at the guided practice, make sure you feel comfortable with it, and bring your questions to class. See you then, everyone.